section of the course. Here we will be learning how to solve differential equations. In A-level maths, uh, if you study further mathematics, you will see differential equations a lot uh, in further chapters, particularly in year 2. But in simple A-level maths, we have to solve differential equations, mainly with separating the variables. So this particular method is called separating variables, where, for example, we see a function like this, b being given derivative dy by dx as a function of x and a function of y. What we can do is separate the variables. That means bringing the x's together and on one side of the equation and taking the y's together to the other side. Now, looking carefully at this, what can we do to bring the x's together? I would multiply both sides by dx, so I will have f of x and dx on the right side and divide by g of y, so that I will have dy over g of y. Now, this has separated the variables now. X's are all on the right side and y's are all on the left. We can read this as basically 1 over g of y. That's fine. That's still the function. At this stage, what we can do is put an integral sign, because this d of y means integrate with respect to y, and this d of x means integrate with respect to x. Okay, so multiplying both sides by dx and dividing by g of y give us this format, and we will have to integrate both sides with respect to corresponding variables. That means solving two integrals. Let's see an example. Here we have d of x in the denominator. Therefore, we have to multiply by d of x so that it comes up, and it will appear on the right side. Therefore, we have to divide both sides of this equation by 1 plus x squared as well. That means we always have to have dy's and dx's up in the numerator. We said that we are going to multiply by d of x. So d of x will come here. I've left the gap here on purpose because we will also have to divide by 1 plus x squared. And that means that this tan of y will have to disappear from the right side and appear on the left. The only way we can do that is by dividing by tan of y. Dividing by tan of y will give us cotan of y. Cotan of y will have to be integrated with respect to y, and x over 1 plus x squared will have to be integrated with respect to x. Okay, so if you don't remember what's the integral of cotan of y, you can check the table of differentiations in the formula booklet. But if, for example, what is cotan? Cotan is cos of x over sine, and cos of x is the derivative of sine. So we have this situation where the derivative of a function is on top of the function. So we said that when we have to integrate this situation here, that means we are going to get log of the function in the denominator. What is the function in the denominator? The denominator is sine of x. That means that we are going to get log of sine for the left hand side integral. Log of sine of x. Okay? We do have to put sign of x within the absolute signs because we don't want to give the log function any negative values. So that's how we deal with that. Now, yes, there is a need for a plus c here, but I'll tell you why we are not going to put it there yet. Okay, let's pay attention to the words in the problem. The words in the problem actually ask us to find a general solution. In other words, this is a general solution. If the question asked us for a particular solution, they would have told us particular. They would have given us a coordinate x and y to substitute into our answers to figure out the value for the constant c. But we don't have that here. Therefore, we are going to have add a constant. Now, I'm not quite finished because what we did here is we only find integral here. Okay, we still have to find this integral for the right hand side. So if you think about what's the integral of x over 1 plus x squared, one more time, if you think carefully, what's the derivative of 1 plus x squared? If this was the function, let's call it, okay, I've called it f of x, doesn't matter. So f dash of x would be 2x. Have in the numerator, or in this integral here, we have only x. So we have a factor of 2 missing. That means once we integrate, if we want to integrate x over 1 plus x squared with respect to x, we can multiply it by 2 as long as we put a factor of a half at the front. That's still our original question. And the integral here now is in the format where we have f dash of x on top of the numerator and f of x in the denominator. And this format was this is the derivative of log of a function. Therefore, the answer here will be log of f of x. Now, what is our f of x here? Our f of x is 1 plus x squared. Therefore, the answer to the integral on the right-hand side is log of 1 plus x squared. Now, this plus c here, we do keep it on the right side. As long as you have 1 plus c, that's that's all that you require, because you can say that yes, there was another plus c on the left hand side, but I brought it here and I subtracted that constant from the constant on the right. So as long as you can combine the left and right constants with each other and only write it once here. Now, usually when we solve differential equations, we don't use the letter C, we use the letter K, but in this case, that's fine. We are going to leave it as C. So, finally, we have logarithm on the left and a logarithm on the right. What can we do? We can take the anti-logarithm here and use e. That means that when you raise e to the power, we can drop the logarithms and write sine of x equals to 1 plus x squared. But don't forget, when you have e raised to the power of two functions, let's say x plus c here, that e to the power of c is multiplied by e to the power of x, right? So some students find this concept rather challenging to understand. So because we have plus c here, that plus c is the same as this plus c here. That means that our constant will become a multiplicative factor, okay, So if you think you were told to simplify the right side, you would add the powers here because these two are multiplied with each other, these two factors, and you would put a plus c here. Now that means that we are just simply going to put a factor, multiplicative factor in front of the 1 plus x squared rather than having a plus sign added together. Now this is called the general solution because we don't have an actual x and y coordinate to substitute and figure out the answer. Actually, there is a mistake here. I integrated this with respect to x. Everything was in terms of y. So let me just correct that. The sign should be in terms of y. This function is in terms of y. So that this is the difference between. Okay, this is the correct solution here. I used the letter X mistakenly here, but you can imagine everything down below here could have been in terms of Y, and it would work out just the same way. Okay, so I'll show you another example next. The function on the left-hand side of the equal sign should be in terms of Y. I've gone ahead and corrected that. But I also forgot about this factor of half in front of the integral. That means there's a half in front of the log on the right hand side. This half in front of the log will simply distribute up here when we have the logarithms. So don't forget that that will go outside the bracket here or outside the absolute sign and will appear on the right side. So I'll show you another example next. One, I quickly wanted to show you that differential equations, when we solve them in terms of general solutions, will have graphs that may look very strange to you. But as long as uh, the coordinate of x and y, we can pick uh, which of these curves will actually fit our differential equation. So that's how specific differential example, we are asked actually to calculate the particular solution to one of these equations. So let's have a look at that. We have to separate variables and multiply and divide by the right factors to have y's on one side of the equation and x's on one side of the equation. Because dx is in the denominator in the left-hand side, we are multiplying by dx. Therefore, we will leave the x's in the denominator on the right side, and we divide by negative 3y minus 2. So that will appear in the denominator on the left-hand side. Actually, we are leaving the negative 3 because that's a constant and that doesn't have any y's in it. So now, at this stage, this should not be so scary to you. What can we do to solve the integral on the left side? That's basically logarithm of y minus 2. There is no coefficients of y there, and we can put that there without a problem. On the right side, the integral will have to be solved by, first of all, applying partial fractions and splitting that into partial fractions. Now I've gone ahead and solved that problem for you, but in most exams, if they're going to test you with partial fractions, they will have it in an integral like so. And you do have to show all the working out, but to save time here, I'm going to just show you the answer. Therefore, now we can integrate the right side with logarithm rules as well. we see the first integral, 1 over x plus 2, will give us logarithm of x plus 2, and the second term here has a factor of 2 on top of the equation, which is the coefficient of x in the denominator. Therefore, we don't have to multiply divided by anything. Only that we need to put the negative sign in front of the log of 2x plus 1. And because we are solving a differential equation, this constant we are going to write as log of k rather than just a plus c. That's fine. Log of k is still a constant, and that's acceptable. Now we can tidy things up with logarithm rules, and I see a negative sign here between these two logs on the right side, so we can divide x plus 2 by 2x plus 1 and write it as 1 log. Now we can drop off the logarithms. Actually, we can take that k and have it as a multiplicative factor here before we drop off the logarithms. And I explained in the previous example, that's why the additional k here, or addition constant, becomes a multiplicative constant, because this is in the final step here, we are applying exponential rules here. And as I explained, f of x here, e to the power of f of x plus c, means that e to the power of c here is multiplied by e to the power of f of x. So yes, the f of x has logarithms in it, therefore e and the logs cancel, and we are just left with f of x, and we are having to multiply by that constant. So e to the power of c is this multiplicative factor here. Now we were also given the values of x and y, so that we can furthermore we can also add and multiply this log of k, because it's an additional log. We can multiply the two by the fractions by k. Now, as I showed you in previous example, if you think about what's happening on the right side and why do we have an addition that turns into multiplication. Next step here is to drop off the logs and just apply the exponential function and write it as so. Now, if you think once again, on the right side, we are taking exponential of logarithm of a function here, and we have a, let's call that log of k a constant c here. Okay, so when you have exponentiation, this log and exponential cancel away, and we are left with the function. But that this this addition in exponential means that e to the power of log of f of x is multiplied by e to the power of c. Therefore, what was addition in this line here is now multiplication in the final line here. So this f of x is multiplied by e to the power c, and we calling this e to the power c a constant, k. Okay, so then we are also told the values of x and y, so that we can actually calculate the value of k, and that's what we will do on the next slide. At this stage, we are simply going to substitute the values that we are given equation and solve for k. You notice is k is going to be 2. Therefore, we can write our final equation as y equals to this expression here, where this factor of k is 2. Now, we had a negative y minus 2, and we took that 2 to the right hand side. So this is one way of writing the same equation. Okay, so this is called the particular solution to the problem where the original question was solved to be here. So this answer on the top is called the general solution, but at the bottom of the page is the particular solution. Alright, so happy practicing, and I'll see you in the next video.